All right. Today we are going to talk about, we will continue for the rest of this class. We will be talking about regression analysis, its extensions. So we will begin with, last time we began with simple linear regression, and then we will continue with simple linear regression and the extensions and the things that matter in simple linear regression and how to use it, how to make a prediction with it. But very important when we talk about simple linear regression is to ask yourself whether the estimates that you have are meaningful, okay? And I will explain that to you. If you think about the very essence of linear regression, we are looking at the relationship between a dependent variable and an independent variable. A dependent variable, for example, will be how much you spend on entertainment. As a dependent variable depends on how much income that you make. How much you spend on clothing will depend on how much income you make, all right? And so the dependent variable here will be how much you spend on clothing. And the independent variable will be how much income that you make. So now we have identified here a dependent variable and an independent variable, and say the values of the dependent variable depend on the values of the independent variable. So y is dependent and x is independent. Now take any two variables. You can ask yourself whether the values of one variable depend on the values of the other variable. And I'll give you an example. Suppose you count the number of vehicles that cross the intersection Bedford Avenue and Crown Street. How many vehicles cross that intersection every day? You count how many babies are born in the hospital downstream in downstate, Brooklyn Hospital. Could you say then that the number of babies born depend on the number of vehicles that cross that intersection? Well, if you take an estimate, if you take a regression estimate and count how many vehicles cross this intersection every day. So every day you take information for the next 300 days. And every day you take information on how many babies are born in downstate hospital. And you ask yourself, could you find a relationship between how many babies are born and how many vehicles cross this intersection? If you do an estimate, you will get some numbers. There's no doubt about that. You will get some numbers. But do those numbers mean anything? Can you use the number of vehicles that cross to predict the number of babies that are born? What we are doing is to test whether there's a meaningful relationship, whether in fact, depending on the number of vehicles, you can also predict the number of babies. So you find a slope and an intercept. What we do is we test that slope to see if the relationship is significant. If the relationship is not significant, then we can argue that there is no relationship between the two variables, okay? So this is part of what we're gonna do today. The next thing we're gonna do then is to ask ourselves, how strong is the relationship? What percentage of the changes in the dependent variable can be explained by changes in the independent variable? All right, so I'm going to share screen with you. And then we're going to Okay, can you see my screen?
Yeah.
Hello?
Yeah.
All right. Okay, so this is simple linear regression. And like I said today, we're going to apply regression analysis to estimate the linear relationship between two variables, okay? And we will also evaluate the significance of the slope, which is to say, is there truly a relationship? So the slope estimate that you obtain, is it meaningful? Okay. And then third, we're going to ask ourselves, how strong is the relationship? What percentage of the changes in the value of the dependent variable can be explained by changes in the independent variable? It will usually not be 100%, but it could be as high as 98%, which means there are hardly any other variables that affect the dependent variable. If it's 40%, then we're saying that there's still 60% of changes in the dependent variable that are not explained by changes in the value of the independent variable. Okay, the dependent variable, as we know, is y, and the independent variable is x. The nature of the relationship can be negative or it can be positive, which we explained the last time. We illustrated that the last time. And then we want to know the size of the relationship. For example, suppose that we say that your expenditure on clothing depends on your income. And so we ask the question, so for each $1 increase in your income, how much would you allocate to clothing? It could be 10 cents. It could be 40 cents. It could be 20 cents. And so that is what the slope will tell you. How strong? What percentage of changes in the value of the dependent variable is explained by changes in the values of the independent variable? Let me make that very clear. Values of the dependent variable can be explained by changes in the values of the independent variable. Okay, so that is what we are going to learn about today. Last time we illustrated this point. What we are looking for is relationship y, whose values depend on the values of x. Now, b represents the rate of change. Okay, if your income changes by, this is income, for example, income changes by $1, then if this is 0.10, that means that your expenditure on clothing will change by 10 cents. All right? Okay. So if your income increases by $1,000, so your expenditure on clothing will change by $100. That's what it is. And A is the constant, which is to say, even if you have a zero income, you are likely to have some clothing. Okay? So all right. So we assume a linear relationship. Y is equal to bx times b times x plus e. Okay. And we also said that we can only obtain an estimate, and the estimate of A is obtained using A hat, and the estimate of B is obtained using B hat. And so these are examples. Like as you see here, we have a positive relationship that is sloping upwards. We did some estimation last time. When we estimated a B hat, we estimated an A hat. Okay, you can see the B hat was 0.261. And so after we do our estimate of A and B, we come up with a model equation. Okay, we come up with a model equation, and this was our model equation. Okay, so we explained this the last time, saying that according to this equation, if a salesperson makes absolutely no call, they'll probably sell $19,900 worth of goods. And for each additional call that they make, they're going to sell an additional $260 worth of goods. Okay, 0.26 of 1,000. Okay, so if a salesperson makes 10 calls, then their sales will be 19,980 plus 0.2606 times 10. And so you can use that to make an estimate. We're going to illustrate that mathematically somewhere along the line. But after you estimate A hat, and after you have your B hat, which is 0.26, this is your B hat, that is your A hat, you create a model equation. You have to create a model equation. Okay? So I just did a recap of our last conversation. Okay, that's what I did. This is why I went through it quickly. So the next question is, now, does our estimate provide us a significant relationship? If your estimate does not provide you a significant relationship, then you cannot say that the values of X affect the values of Y. No, you just cannot say that. All right? This is another example. For example, this is about dividend policy. Companies that declare dividends, do they, the price of their stock, does it affect the price of their stock? Companies that declare dividends, does it affect the price of their stocks? Okay, this is another example that we estimated here. And we said that the basic price of this a share of stock is about $26. But for each $1 of dividend, then the price of the stock would increase by $2.41. That is what our model equation here is telling us. Okay, here is where we estimate the B hat, and we also estimated A hat. Okay, and so with A hat and B hat, we create a model equation, and I'm going to reinforce it here. Okay, this is B hat. This is A hat, okay, which is the constant. All right. Once you use these two values, you create a model equation. Okay. And so, for example, if dividends of this company is $2 per share, then the price of the share of stock of that company will be 26.55 times plus 2.41 times 2, which means that for a company that pays $2 per share, the average price of the stock will be $31.37. Am I making sense? Hello?
Yeah.
You making sense? Okay. So you use the A hat and the B hat, which are estimates of the equation, to make a prediction. All right. So now the question is, how strong is the relationship? Okay. How strong is the relationship? What percentage of changes in the values of the dependent variable can be explained by changes in the values of the independent variable? In order to calculate this, how strong the relationship is, we use what we call a coefficient of determination. Okay, this is very critical. Very critical that you say exactly what it is, a coefficient of determination. And that coefficient of determination is symbolized with r to the power 2, r squared. So how do you calculate r squared? Okay. R squared is b hat times the equation that you already used, except that you have y minus y bar squared here, which is equal to 65.69%. When you calculate it mathematically, you are going to get a decimal, which is 0.6569. And of course, you make it 65.69%. So 65.69% of changes in stock prices is explained by changes in the amount of dividends. All right? Very simple. It means that when investors go to buy stock, they are not looking only at whether the company is paying dividends. They are looking at other possible variables. It could be the riskiness of the company, okay? It could also be that the investors that invest in a particular company have other objectives. They might not want to be receiving dividends. They might want the company to grow and pay less dividends. There are other factors, a whole bunch of other factors, okay? And so it means that as much as 34% of the changes in the price of the stocks of the company are not entirely explained by the desire for investors to have dividends. Here's another example. The cost of maintenance of a bus as a function of age. So we know very well that the cost of maintenance depends on also the age. Like the older your car gets, your vehicle gets, the more money you are likely to spend on the maintenance. So we specify a model, M, as a dependent variable, which is the maintenance expense per year, and B as the rate of change. For example, for each additional year, how much additional money are you going to spend on the maintenance of a vehicle, okay? So A represents the fixed cost. You have to maintain a vehicle whether or not, I mean, even if you leave it there from the moment you buy it, you're going to change oil, you're going to put in new oil, you're going to do other things to maintain the vehicle. And B is additional cost per additional year of use. Okay, and we obtain data. Okay, we use the same model that we use to estimate for other kinds of problems. Okay, so we do the calculations there. I'm not going to require you to do those calculations, not yet. When we were done, this is what we have. Okay, we have a model equation that says the minimum cost of maintaining a vehicle is $329, which is our A hat, plus an additional $15.59 per year for a bus that is 8 years old. The annual cost of maintenance will be $329 plus 15.598 times 8, which is for vehicles that are 8 years old, we are looking at an annual maintenance cost of $454. Now, what factors, what percentage of changes in maintenance costs is explained by age, which is changes in the age, okay? And our calculation here is that 41.1418% of changes in maintenance is explained by changes in the age. Now you can see that when we did our calculation, what we got was a decimal point, 0.4118. And you convert that to percentage, becomes 41.418%. Okay, so again, that means that if only 41% of changes in the maintenance cost of a vehicle is explained by changes in age, then there are other factors. Okay, Other factors could be how much mileage, okay? How much mileage that you put in the vehicle. How do you use the vehicle? If you are driving this vehicle in places that have a lot of potholes, which means the environment could be a factor, all right? How many miles that you put on the vehicle, okay, per year, could be a factor. And so there are other factors that affect maintenance costs. But at this level, we are still dealing with simple linear regression where we're dealing with only one independent variable, okay? From next week, we're going to get into multiple regression. So you will see this example again with multiple variables. All right. Okay, so this is where we solve the problem to get the model equation. All right. So now we are going to ask ourselves, is the relationship meaningful? All right. Does our estimate provide us information? So I'm going to just create a new heading. Okay, I'm going to say, call this test of hypothesis. Calculated relationship meaningful. Okay, and so the test for the significance of the relation between y, the dependent variable, and x, dependent variable. And so you test for the significance of the slope. That's what you do. You test for the significance of the slope. You use z test or the t-test. Okay. All right. So I need to make clear where we are going. We are moving to the next stage. I'm moving to the next stage. All right. So now, you know that you are testing the hypothesis for the slope against the population because you use the sample. So you say to yourself, if the relationship is meaningful, okay? So I'm going to go back to this, okay? If B equals to 0, then X does not have a significant effect on Y. That is to say that the independent variable does not significantly affect the dependent variable. If B is 0, okay? That is to say, if the regression line is flat, then there's no relationship, okay? All right. So here, again, this is the mathematical formula for calculating the statistic, but let's focus on the basic concept, okay? So you state a hypothesis, okay? So I'm going to move this. All right. So you have to begin the test of hypothesis the normal way. You state the null and alternate hypothesis. The null hypothesis is that B is equal to 0. That is, the slope of the regression is 0, which means there's no relationship. Okay? There's no significant relationship. Okay? If B is 0. Now, remember we stated an equation. Okay? So let's remember the equation. Y is equal to A plus Bx plus E. So this is what you are looking at. Okay? You are looking at this, you're asking yourself if this B here is equal to 0. If B is equal to 0, you can see very well that B times X will be 0, which means that there is no significant effect on Y from X if B is 0, because that second part of that equation will be 0. So Y is a constant value. X does not affect Y. Okay, so that is our hypothesis. Okay, let me see if I can replace that with a symbol so that we don't get confused. All right, so we're looking at B, the same, but I put it in Greek form. Okay, so our objective is to ask ourselves if beta is equal to 0. If beta is equal to 0, then there is no significant relationship between X and Y. Okay, the alternate hypothesis, this is the alternate hypothesis H1, which we already learned how to test the hypothesis. And so the alternate hypothesis is that B is not equal to 0, and therefore there is a significant relationship. Okay? All right. Okay. Now, once you state the null and alternate hypothesis, you state a level of significance. Since we're using the z-test, okay, we identify a test statistic. So let me, for the sake of this argument, use a 0.205. And so our z star, the critical z, which we have talked about before, the critical z, equal to 1.96. Okay, look that up in the table. I think we went through how to go identify that. So we identified the test statistic. All right. So for a particular problem, we estimated B hat to be 15.598. So we calculated Z, which is the calculated Z. Okay. And if Z, the calculated Z is greater than Z star, then we reject the null hypothesis. And the calculation of Z is B minus B hat. And our hypothesis is that B is 0. Okay. back here and take okay. Okay. So if null hypothesis is that beta is equal to 0. So we subtract that from the b hat that we estimate and divide by the standard error of b hat. The standard error is like we divide by the standard deviation. We divide by the standard error of b hat. And here, the standard error of b hat is something that we calculate, and this is the formula for it if you're going to calculate it by hand. But we're not calculating it by hand. And so you can try that by yourself and demonstrate to yourself that that is the result. And so how do we proceed? All right. So like I said, this is the hypothesis test. The null hypothesis is that b is equal to 0. The actual b is equal to 0. And so the slope is 0, and changes in the value of the independent variable do not significantly affect changes in the value of the dependent variable. The alternate hypothesis is that b is not 0, which means we're saying that there is a significant relationship between the dependent and the independent variable. So, like I said, I'm not going to burden you in any test or whatever with those technical calculations. I mean, they should at this level of studying statistics. But we have here a printout. And the example we are using is an example of family size and food expenditure. How much does a family spend on food expenditure? And we are theorizing that the amount of money that a family spends on food, which is the dependent variable, depends on the size of the family. Does it make sense? Hello?
Say that again, Professor.
Okay. We are theorizing that there's a relationship between the amount of money a family spends on food and the size of the family.
Okay.
Does it make sense to you?
Yeah, it makes sense.
Okay. And so our model, when we did the estimation that we went through, as you can see, we went through an estimation process. And so we have a printout. Okay. And this printout says that the constant value is 3.379 in the hundreds of dollars. Okay. And the size of the family, which gives you the slope, is 0.414. All right. Okay. So for each additional dollar, for each additional person in the family, the additional expenditure on food is 41 cents. Okay. The additional expenditure on food is 41 cents. And so the Z value for this test is 17 for the constant and 8 for the slope. Okay. And so we ask ourselves, is there a relationship? Okay. So this is the model equation. You can see that?
Yeah, I can see that.
Okay.
Yeah.
And the standard error is 0.048 for the slope. Okay, the sample size is 46, and we're using a 0.005 level of significance, which gives us a critical Z value of 2.576. We learn how to find critical values based on the level of significance. Okay. And so the null hypothesis is that family size does not matter, does not affect amount spent on food. That is the null hypothesis. Remember, we said that this estimated B truly population-wise is 0. That is a hypothesis, that the slope is a 0. which is that the family size does not matter. Family size does not affect amount spent on food. The alternate hypothesis is that family size does matter. It does significantly affect the amount spent on food. So we calculate a Z. This is our calculated Z. Okay, the calculated Z is the hypothesis that beta minus B hat, that is 0 minus B hat, you see 0 minus B hat, which is what we estimate, divided by the standard error of B, which you see in the estimation that we did, gives us 8.625. All right, let's go back to it. You see the constant, the slope, you see the standard error, 0.048, and we get exactly that. So when you see this in a printout, I expect for you to be able to interpret it and put it in this form, and then make a decision. The decision rule, as you learned earlier, for hypothesis testing is if the calculated Z is greater than or equal to the critical Z star, then we reject the null hypothesis. If the calculated Z is less than the Z star, we cannot reject the null hypothesis. Therefore, in this problem, what is the decision? The decision is that the calculated Z, 8.625, is greater than the critical Z of 2.576. Therefore, we reject the null hypothesis that family size does not matter. So what is your conclusion? If you reject the null hypothesis that family size does not matter, what is your conclusion? Hello? Can somebody respond to me?
It does not matter.
We rejected the null hypothesis. You remember there are two hypotheses.
Mm-hmm.
The null
Okay.
hypothesis that says family size does not matter,
Does not matter. Mm-hmm.
and the alternate hypothesis that family size does matter. So now you
Okay.
have rejected the null hypothesis that family size does not matter. What is the conclusion then?
Then family size does matter.
That family size does matter. You get the point?
Yes.
Okay. I mean, once you reject one, then that means you're accepting the other one.
Correct.
It does make a lot of sense, doesn't it?
Yes, it makes sense.
Okay, because you have two alternatives. It's one or the other. All right. So today we went through that process so that we know now how to interpret regression models. Okay. This is just like an outline of the example. That this is the solved example, and this solved example should actually come at the beginning here. Okay. Should come there. But I'm going to fix it so that it's more meaningful. So does anybody have any questions for me?
No.
No, Professor, I need to speak with you
Okay.
after class.
After class?
Yes.
Okay. All right. We can make it very simple.
Mm-hmm.
What's your name?
Paula Greenwich.
Paula Greenwich. Okay. Miss Murray. Is that Murray?
Yes.
Okay. Do you have any questions to ask?
No.
Okay. So then I'm going to ask you to leave so that me and Paula will not have to set up another Zoom call.
Okay. Well, have
All
a
right.
good night, guys.
All right.
Okay.
Good night.
Thank you. Bye.
Okay. All right, Paula, before we start, I'm going to suspend.
You too. Thanks.